Chapter 6 Flight Manuevers Introduction Flying. A weight shift control (WSC) aircraft is not like driving an automobile on the highway. It is also different from operating the controls of an airplane. A WSC pilot holds the control bar, which is a structural component of the wing, in his or her hands. This wing is attached to the carriage and freely rotates laterally and longitudinally about the hang point. Therefore, the feel of the WSC is completely different from other aircraft because there are no movable control surfaces actuated through push/pull rods or cables connected to a separate control actuator, such as a stick or yoke. The pilot feels forces on the wing through the control bar, which is part of the wing structure with no mechanical advantage. Simply, the feel of the WSC is different from other aircraft, but the basic Flight maneuvers are similar. Practicing the basics with precision and understanding the effects on the pilot and the aircraft develop a feel for the aircraft in Flight so the pilot can concentrate on the flying mission at hand and not on the mechanical movements. The ability to perform any assigned maneuver is only a matter of obtaining a clear visual and mental conception of it so that perfect performance is a habit without conscious effort. Begin with the Flight basics to build a foundation for precision flying. Takeoff/landings and emergency maneuvers are covered in later chapters. All flying tasks are based on the four fundamental Flight maneuvers. Straight and level Flight turns, climbs, descents. Controlled Flight consists of either one or a combination of these basic maneuvers. Effects and the use of the controls. In using the Flight controls, the results should be looked at in relation to the pilot. The pilot should always be considered the center of movement of the aircraft or the reference point from which the movements are judged and described. The important concept and a foundation for all Flight maneuvers is not to think of the controls in terms of up or down in respect to the Earth. This is only a relative state to the pilot. Controls need to be thought of in relation to the pilot, so that the control used can be for any Flight attitude, whether climbing, diving, banking, or a combination of these. Sideways pressure applied by moving the control bar to the left lowers the right wing in relation to the pilot. Moving the control bar to the right lowers the left wing in relation to the pilot. This is roll control as discussed in Chapter 2, Aerodynamics. Figure 6.1, pushing and forward pressure applied to the control bar results in the WSC aircraft's nose rising in relation to the pilot slowing down the WSC, while pulling in or back pressure results in the nose lowering in relation to the pilot increasing speed of the WSC. At the same trim speed, increasing the throttle results in the nose remaining at the same level in relation to the pilot but raising pitch with increased throttle and lowering pitch with decreased throttle in relation to the Earth's horizon. Both control bar and throttle affect pitch in relation to the Earth's horizon. This is pitch control, as discussed in Chapter 2, Aerodynamics. Figure 6.2. Feel of the aircraft. All WSC aircraft controls have a natural live pressure while in Flight and will remain in a neutral position of their own accord if the aircraft is trimmed properly. The pilot should think of exerting a force on the controls against this live pressure or resistance. It is the duration and amount of force exerted on the control bar that affects the controls and maneuvers the WSC aircraft. The actual amount of the control input is of little importance, but it is important that the pilot maneuver the aircraft by applying sufficient control pressure to obtain a desired result, regardless of how far the control bar is actually moved. The controls should be held lightly, not grabbed and squeezed. A common error for beginning pilots is a tendency to tightly grip the bar. This tendency should be avoided as it prevents the development of feel, which is an important part of aircraft control. Figure 6.3. However, for WSC aircraft, the controls do need to be gripped during moderate and severe turbulence to make sure the wing does not get ripped out of the pilot's hands. This is why flying a WSC aircraft in turbulence requires strength and endurance. It can be fatiguing if the pilot is not used to or in shape for this type of flying. The initial Flight training should be done in calm conditions so the student can use a soft touch on the controls to develop the feel for the WSC aircraft. The ability to sense a Flight condition is often called feel of the aircraft, but senses in addition to feel are also involved. Sounds inherent to Flight are an important sense in developing feel. The air that rushes past an open Flight deck can be felt and heard easily within the tolerances of the practical test standards, TTS, of plus or minus 10 knots. When the level of sound increases, it indicates that airspeed is increasing. In addition to the sound of the air rushing past is also felt unless an effective wind screen is placed in front of the pilot blocking the wind. Figure 6.4. The power plant emits distinctive sound patterns in different conditions of Flight. The sound of the engine in cruise Flight sounds different from the sound in a glide or a climb. Overall, there are three sources of actual feel that are very important to the pilot. 1. The faa-h-8083-5 source is the pilot's own body as it responds to forces of acceleration. The g-loads, as discussed in Chapter 2, imposed on the airframe are also felt by the pilot. Centripetal acceleration forces the pilot down into the seat or raises the pilot against the seat belt. Radial accelerations, although minor for WSC aircraft, are caused by minor slips or skids in uncoordinated flight and shift the pilot from side to side in the seat. These forces are all perceptible and useful to the pilot. Flight time plus the pilot's desire to feel the aircraft provides the pilot an excellent feel for the aircraft and the ability to detect even the smallest change in flight. A goal for any pilot should be to constantly develop a better feel for their aircraft. 2. The response of the controls to the pilot's touch is another element of feel, and is one that provides direct information concerning airspeed. 3. Another type of feel comes to the pilot through the airframe. It consists mainly of vibration. An example is the aerodynamic buffeting and shaking that precedes a stall. Different airspeeds and power settings can also provide a subtle feel in aircraft vibrations. Kinesthesia, or the sensing of changes in direction or speed of motion, is one of the most important senses a pilot can develop. When properly developed, kinesthesia can warn the pilot of changes in speed and/or the beginning of a settling or mushing of the aircraft. The senses that contribute to feel of the aircraft are inherent in every person. However, feel must be developed. It is a well-established fact that the pilot who develops a feel for the aircraft early in flight training has little difficulty with advanced flight maneuvers. Attitude flying by attitude means visually establishing the aircraft's attitude with reference to the natural horizon. Attitude is the angular difference measured between an aircraft's axis and the Earth's horizon. As discussed in Chapter 2, Aerodynamics, pitch attitude is the angle formed by the longitudinal axis, and bank attitude is the angle formed by the lateral axis. Rotation about the aircraft's vertical axis, yaw, is termed an attitude relative to the aircraft's flight path, but not relative to the natural horizon. In attitude flying, aircraft control is composed of three components. 1. Bank control, control of the aircraft about the longitudinal axis to attain a desired bank angle in relation to the natural horizon. This can be easily seen in a WSC aircraft by looking at the angle the front tube makes with the horizon. Figure 6.5. 2. Pitch control, control of the aircraft about the lateral axis to raise and lower the nose in relation to the natural horizon. 3. Power control, used when the flight situation indicates a need for a change in thrust, which at a constant speed raises and lowers the nose in relationship to the horizon, similar to pitch control. Straight and level flying straight and level is the most important flight maneuver to master. It is impossible to emphasize too strongly the necessity for forming correct habits in flying straight and level. All flight is in essence a deviation from this fundamental flight maneuver. It is not uncommon to find a pilot whose basic flying ability consistently falls just short of minimum expected standards, and upon analyzing the reasons for the shortcomings discover that the cause is the inability to fly straight and level properly. In learning to control the aircraft in level flight, it is important that the control forces be exerted just enough to produce the desired result. Some wings are more responsive than others. The student should learn to associate the apparent movement of the control bar with the response in pitch and roll. In this way, the student can develop the ability to regulate the change desired in the aircraft's attitude by the amount and direction of forces applied to the controls without the necessity of referring to outside references for each minor correction. Straight and level flight is flight in which a constant heading and altitude are maintained. It is accomplished by making immediate and measured corrections for deviations in direction and altitude from unintentional slight turns, descents, and climbs. Level flight is a matter of consciously fixing the relationship of the position of something on the aircraft, used as a reference point with a point on the horizon. In establishing the reference point on the aircraft, place the aircraft in the desired position and select a reference point. A typical reference point on the WSC aircraft is a point on the front tube. The WSC aircraft reference point depends on where the pilot is sitting, the pilot's height, whether short or tall, and the pilot's manner of sitting. It is therefore important when establishing this relationship, the pilot sit in a normal manner, otherwise the points will not be the same when the normal position is resumed. Figures 6-6 and 6-7, straight and level flight should faa-h-8083-5 be practiced in calm air where the control movements determine the actual movement through the air and air movement has minimal effect on the aircraft's altitude and direction. A trim speed needs to be set if the WSC aircraft has an in-flight trim system or the trim speed set on the ground is used. The throttle is adjusted so the aircraft is flying level, not climbing or descending. This can be determined by looking at the altimeter or the vertical speed indicator, if so equipped. The throttle setting is the control for maintaining level flight for a specific weight, loading, trim speed, and density altitude. Level flight is maintained by selecting some portion of the aircraft's nose as a reference point, and then keeping that point in a phi-crossed position relative to the horizon. Using the principles of attitude flying, that position should be cross-checked occasionally against the altimeter to determine whether or not the throttle setting and pitch attitude are correct. If altitude is being gained or lost, the pitch attitude should be readjusted with the throttle in relation to the horizon. Then, recheck the altimeter to determine if altitude is being maintained and adjust the throttle accordingly. The throttle setting for this condition should be noted in all future changes in weight, trim speed, and density altitude reference to this known throttle setting. After level flight is mastered in calm air, it can be practiced in air that is moving, minor turbulence or active air. The throttle settings for similar weight, trim, and density altitude are the same, but more pilot input is required to maintain a constant altitude. The throttle is used to maintain a selected distance above the reference point for local air movement, but the pitch pressure, nose up or nose down, is used to control this attitude for shorter duration air disturbances. Typically, updrafts or thermals raise the nose of the aircraft and downdrafts at the edge of thermals lower the nose of the aircraft. For minor updrafts, the nose is lowered by pitch control input by the pilot, slightly increasing the speed of the aircraft to keep the pitch at a constant level. In moderate to severe updrafts, the throttle can be reduced to assist in maintaining a reasonably constant pitch angle with the horizon. Similarly, for minor downdrafts that lower the nose is raised by pitch control input by the pilot, slightly decreasing the speed of the aircraft to keep the pitch at a constant level. An additional caution for raising the nose and decreasing the speed is that raising the nose too high could stall the aircraft. Therefore, caution must be exercised in moderate downdrafts not to reduce the speed too much to approach a stall speed/critical angle of attack. Similar to reducing the throttle in updrafts to reduce pitch angle, increasing the throttle typically increases the pitch angle. Figure 6.8, WSC aircraft can use the front tube as a reference to align perpendicular with the horizon and the wings leveled. It should be noted that any time the wings are banked even slightly, the aircraft will turn. The front tube can be used as an indicator to determine turn rate. If the bar is moving side to side to any established reference point, the aircraft is banked and should be corrected to eliminate any turn. The objective of straight and level flight is to detect small deviations from level flight as soon as they occur, necessitating only small corrections. Straight and level flight requires almost no application of control pressures if the aircraft is properly trimmed and the air is smooth. For that reason, pilots must not form the habit of constant, unnecessary control movement. Pilots should learn to recognize when corrections are necessary, and then make a measured response easily and naturally. Common errors in the performance of straight and level flight are: attempting to use improper reference points on the aircraft to establish attitude, forgetting the location of selected reference points, too tight a grip on the flight controls resulting in over-control and lack of feel, improper scanning and or devoting insufficient time to outside visual reference, head in the flight deck, fixation on the nose, pitch attitude, reference point only, unnecessary or inappropriate control inputs, failure to make timely and measured control inputs when deviations from straight and level flight are detected, inadequate attention to sensory inputs in developing feel for the aircraft. Trim control. The use of trim systems relieves the pilot of the requirement to exert pressures for the desired flight condition. An improperly trimmed aircraft requires constant control pressures, produces pilot tension and fatigue, distracts the pilot from scanning, and contributes to abrupt and erratic aircraft control. Most WSC aircraft have a ground-adjustable pitch/speed trim system that adjusts the carriage hang point on the wing keel that is set for the desired speed. Some WSC aircraft have additional pitch control systems that can adjust the trim speed and flight as described in Chapter 3, Components and Systems. There is no yaw trim, but the roll trim is usually adjusted on the ground for a wing that has a turn in it. Roll trim is usually adjusted so the wing flies straight in cruise flight. This is a balance between the full power torque of the engine wanting to turn it in one direction and minimum power when the WSC aircraft is in a glide. WSC pilots usually have to exert some pilot roll input for high-power engines at full power climb to fly straight because of the engine turning effect. Level turns. A turn is made by banking the wings in the direction of the desired turn. A specific angle of bank is selected by the pilot, control pressures are applied to achieve the desired bank angle, and appropriate control pressures are exerted to maintain the desired bank angle once it is established. Banking is performed with the following steps. Figure 6.9, entering a turn A. Straight FLIght B. Pilot applies sideways pressure to the control bar, shifting the weight towards the direction of the desired turn, initiating the bank. C. Turn is established and maintained by moving the control bar back to the center position. Exiting a turn. D. Pilot is maintaining stabilized bank and a resultant turn. E. Pilot shifts weight to opposite side to initiate exit out of the turn. F. Straight FLIght is established and maintained by moving the control bar back to the center position. Coordinating the controls. Flight controls are used in close coordination when making level turns. Their functions are: the WSC is banked with side-to-side pressure with the control bar, and the bank angle established determines the rate of turn at any given airspeed. The throttle provides additional thrust used to maintain the WSC and level FLIght. Pitch control moves the nose of the WSC aircraft up or down in relation to the pilot and perpendicular to the wings. Doing this sets the proper pitch, attitude, and speed in the turn. Turns are classified to determine the bank angle as follows. Shallow turns are those in which the bank is less than approximately 20 degrees. Medium turns are those resulting from a degree of bank that is approximately 20 degrees to 45 degrees. Steep turns are those resulting from a degree of bank that is 45 degrees or more. Changing the direction of the wings lift toward one side or the other causes the aircraft to be pulled in that direction. When an aircraft is flying straight and level, the total lift is acting perpendicular to the wings and to the earth. Figure 6.10, as the WSC is banked into a turn, the lift then becomes the resultant of two components. 1. The vertical lift component continues to act perpendicular to the earth and opposes gravity. 2. The horizontal lift component, centripetal, acts parallel to the earth's surface and opposes inertia, apparent centrifugal force. These two lift components act at right angles to each other, causing the resultant total lifting force to act perpendicular to the banked wing of the aircraft. It is the horizontal lift component that actually turns the WSC aircraft. Figure 6.10, shallow turns are accomplished by moving the control bar to the side slightly, waiting for the wing to roll the desired amount, and then releasing the side pressure on the control bar back to the center position. The WSC aircraft will stabilize in the turn with no control pressures required. During a shallow turn, there is no significant increase in airspeed or g-forces that can easily be noticed by the student. Figure 6.11, once a shallow turn is initiated, it is a good practice to be stabilized at a constant bank and then exit to a predetermined heading. To exit the shallow turn, opposite sideways pressure must be put on the control bar to bring the WSC aircraft back to level FLIght. For higher bank turns, the entry speed should be well above 1.3 times the stall speed, which increases significantly in higher bank turns. As an example, at least 1.5 times the stall speed should be the entry speed for a 40-degree bank turn to maintain the 1.3 times the stall speed safety margin. Wings with a trim speed of 1.3 times the stall speed require an increase in speed slightly. In all constant altitude, constant airspeed turns, it is necessary to increase the angle of attack of the wing when rolling into the turn by pushing out on the control bar. This is required because part of the vertical lift has been diverted to horizontal lift. Thus, the total lift must be increased to compensate for this loss. Similarly, the throttle must be increased to maintain the same altitude in steeper banks. The additional load or g-force in a medium bank turn is felt as the pilot is pushed down on the seat with enough force for this effect to be noticed. After the bank has been established in a medium turn, all side-to-side roll pressure applied may be relaxed, but forward pressure to maintain a higher angle of attack is still necessary in a steeper bank. The WSC aircraft remains at the selected bank with no further tendency to roll back to level since all the forces are equalized. During the turn, roll, pitch, and throttle controls are adjusted to maintain the desired bank angle, speed, and level altitude. Coordinated FLIght is the coordination of the three controls to achieve a smooth turn to the desired bank angle while maintaining a constant speed and altitude. The rollout from a turn is similar to the roll-in, except FLIght controls are applied in the opposite direction. As the angle of bank decreases, the pitch pressure should be relaxed as necessary to maintain speed and the throttle decreased to maintain altitude. Since the aircraft continues turning as long as there is any bank, the rollout must be started before reaching the desired heading. The amount of lead required to roll out of the desired heading depends on the degree of bank used in the turn. Normally, the lead is 1/2 the degrees of bank. For example, if the bank is 30 degrees, lead the rollout by 15 degrees. As the wings become level, the control pressures should be smoothly relaxed so that the controls are neutralized as the aircraft returns to straight and level FLIght. As the rollout is being completed, attention should be given to outside visual references to determine that the wings are being leveled and the turn stopped. To understand the relationship between airspeed, bank, and radius of turn, it should be noted that the rate of turn at any given true airspeed depends on the horizontal lift component. The horizontal lift component varies in proportion to the amount of bank. Therefore, the rate of turn at a given true airspeed increases as the angle of bank is increased. On the other hand, when a turn is made at a higher true airspeed at a given bank angle, the inertia is greater and the horizontal lift component required for the turn is greater, causing the turning rate to become slower. Therefore, at a given angle of bank, a higher true airspeed makes the radius of turn larger because the aircraft is turning at a slower rate. Figure 6.12. When changing from a shallow bank to a medium bank, the airspeed of the wing on the outside of the turn increases in relation to the inside wing as the radius of turn decreases. The additional lift developed because of this increase in speed of the wing balances the inherent lateral stability of the aircraft. At any given airspeed, roll pressure is not required to maintain the bank. If the bank is allowed to increase from a medium to a steep bank, the radius of turn decreases further. A steep bank is similar to a medium bank, but all factors increase. Roll and pitch control pressures must increase, throttle must increase further to maintain altitude, and the g-forces increase significantly. Students should build up to steep bank turns gradually after perfecting shallow and medium bank turns. Do not exceed the bank angle limitation in the pilot's operating handbook, POH. The pilot's posture while seated in the aircraft is very important, particularly during turns. It affects the interpretation of outside visual references. Pilots should not lean away from the turn in an attempt to remain upright in relation to the ground rather than ride with the aircraft. This should be a habit developed early so that the pilot can properly learn to use visual references. Beginning students should not use large control applications because this produces a rapid roll rate and allows little time for corrections before the desired bank is reached. Slower, small control displacement roll rates provide more time to make necessary pitch and bank corrections. As soon as the aircraft rolls from the wing's level attitude, the nose should also start to move along the horizon, increasing its rate of travel proportionally as the bank is increased. The following variations provide excellent guides. If the nose moves up or down when entering a bank, excessive or insufficient pitch control is being applied. During all turns, the controls are used to correct minor variations as they are in straight and level flight. Instruction in level turns should begin with changing attitude from level to bank to level, and so on with a slight pause at the termination of each phase. This pause allows the WSC to free itself from the effects of any misuse of the controls and ensures a correct start for the next turn. During these exercises, the idea of control forces, rather than movement, should be emphasized by pointing out the resistance of the controls to varying forces applied to them. Common errors in the performance of level turns are: failure to adequately clear the area before beginning the turn, attempting to sit up straight in relation to the ground during a turn, rather than riding with the aircraft, failure to maintain a constant bank angle during the turn, gaining proficiency in turns in only one direction, failure to coordinate the angle of attack to maintain the proper airspeed, failure to coordinate the use of throttle to maintain level flight, altitude gain/loss during the turn. Climbs and climbing turns. When an aircraft enters a climb, it changes its flight path from level flight to an inclined plane or climb attitude. As discussed in Chapter 2, weight in a climb no longer acts in a direction perpendicular to the flight path. It acts in a rearward direction. This causes an increase in total drag, requiring an increase in thrust, power, to balance the forces. An aircraft can only sustain a climb angle when there is sufficient thrust to offset increased drag, therefore, climb is limited by the thrust available. Figure 6.13, like other maneuvers, climb should be performed using outside visual references and flight instruments. It is important that the pilot know the engine power settings and pitch attitudes that produce the following conditions of climb. Normal climb, performed at an airspeed recommended by the aircraft manufacturer. Normal climb speed is generally the WSC best rate of climb, VY, speed as discussed below. Faster airspeed should be used for climbing in turbulent air. Best rate of climb, VY, the airspeed at which an aircraft will gain the greatest amount of altitude in a given unit of time. Maximum rate of climb in feet per minute, FPM. The VY made at full allowable power is a maximum climb. This is the most efficient speed because it has the best lift over drag ratio for the aircraft. This speed is also the best glide ratio speed used for going the greatest distance for the amount of altitude, as discussed later in this chapter. Each aircraft manufacturer is different, but a good rule of thumb is that the VY is 1.3 times the stall speed. It must be fully understood that attempts to obtain more climb performance than the aircraft is capable of by increasing pitch attitude results in a decrease in the Rate of altitude gain. Trim is usually set at the VY or higher. Best angle of climb, VX, performed at an airspeed that will produce the most altitude gain in a given horizontal distance. Best VX airspeed is lower than VY but higher than minimum controlled airspeed. The VX results in a steeper climb path, although the aircraft takes longer to reach the same altitude than it would at VY. The VX, therefore, is used in clearing obstacles after takeoff. Since the VX is closer to the stall speed, caution should be exercised using this speed to climb so as not to stall the WSC aircraft close to the ground with potentially catastrophic consequences. Figure 6.14, climbing flight requires more power than flying level, as described in Chapter 2. When performing a climb, the normal climb speed should be established and the power should be advanced to the climb power recommended by the manufacturer. As the aircraft gains altitude during a climb, the engine has a loss in power because the same volume of air entering the engine's induction system gradually decreases in density as altitude increases. During a climb, a constant heading should be held with the wings level if a straight climb is being performed, or a constant angle of bank and rate of turn if a climbing turn is being performed. To return to straight and level FLI, when approaching the target altitude, increase the speed to the cruise setting, if different, and decrease throttle for level FLI. After the aircraft is established in level FLI at a constant altitude and the desired speed, the aircraft should be trimmed, if equipped with an FLI trim system. In the performance of climbing turns, the following factors should be considered. With a constant power setting, the same pitch attitude and airspeed cannot be maintained in a bank as in a straight climb due to the increase in the total lift required. The degree of bank should not be too steep. A steep bank significantly decreases the rate of climb. The bank should always remain constant. At a constant power setting and turning while climbing, the WSC aircraft climbs at a slightly shallower climb angle because some of the lift is being used to turn. Attention should be looking at outside references and scanning for traffic with no more than 25% of the time looking at inside FLI deck instruments. There are two ways to establish a climbing turn. Either establish a straight climb and then turn, or enter the climb and turn simultaneously. Climbing turns should be used when climbing to the local practice area. Climbing turns allow better visual scanning, and it is easier for other pilots to see a turning aircraft. In any turn, the loss of vertical lift and increased induced drag due to increased angle of attack becomes greater as the angle of bank is increased. So, shallow turns should be used to maintain an efficient rate of climb. All the factors that affect the aircraft during level, constant altitude, turns affected during climbing turns or any other maneuver. Common errors in the performance of climbs and climbing turns are: a bank angle too high to achieve an efficient climb, a speed too high to achieve an efficient climb rate, a speed that is too low, attempting to exceed the aircraft's climb capability, inability to keep pitch and bank attitude constant during climbing turns, attempting to establish climb pitch attitude by referencing the airspeed indicator, resulting in chasing the airspeed. Descents and descending turns. When an aircraft enters a descent, it changes its FLI path from level to an inclined plane. It is important that the pilot know the power settings and pitch attitudes that produce the following conditions of descent. Partial power descent. The normal method of losing altitude is to descend with partial power. This is often termed cruise or en route descent. The airspeed and power setting recommended by the aircraft manufacturer for prolonged descent should be used. The target descent rate should be 400 to 500 fpm. Steep approach. The normal maneuver used to descend at a steep angle. This is typically used to descend for landing if higher than expected upon approaching the runway. The throttle is set to idle and the airspeed is increased so the excessive drag allows the WSC aircraft to descend at the steepest angle. The control bar is pulled in to achieve this steep approach. The further the bar is pulled in, the steeper the descent rate. Each WSC aircraft is different, but pulling the control bar to the chest may be necessary to achieve the required angle. Descent at minimum safe airspeed. A nose-high descent. This should only be used for unusual situations such as clearing high obstacles for a short runway in an emergency situation. The only advantage is a steeper than normal descent angle. This is similar to the best angle of climb speed and should only be used with caution because stalling near the ground could have catastrophic consequences for the pilot, passenger, and people/property on the ground. Glide. A basic maneuver in which the aircraft loses altitude in a controlled descent with little or no engine power. Forward motion is maintained by gravity pulling the aircraft along an inclined path, and the descent rate is controlled by the pilot balancing the forces of gravity and lift. Figure 6.15, although glides are directly related to the practice of power-off accuracy landings, They have a specific operational purpose in normal landing approaches and forced landings after engine failure. Therefore, it is necessary that they be performed more subconsciously than other maneuvers because most of the time during their execution, the pilot gives full attention to details other than the mechanics of performing the maneuver. Since glides are usually performed relatively close to the ground, accuracy of their execution, the formation of proper technique, and habits are of special importance. The glide ratio of a WSC aircraft is the distance the aircraft, with power off, travels forward in relation to the altitude it loses. For instance, if it travels 5,000 feet forward while descending 1,000 feet, its glide ratio is said to be 5:1. The glide ratio is affected by all four fundamental forces that act on an aircraft: weight, lift, drag, and thrust. If all factors affecting the aircraft are constant, the glide ratio is constant. Although the effect of wind is not covered in this section, it is a very prominent force acting on the gliding distance of the aircraft in relationship to its movement over the ground. With a tailwind, the aircraft glides farther because of the higher ground speed. Conversely, with a headwind, the aircraft does not glide as far because of the slower ground speed. Variations in weight for an aircraft with a rigid wing do not affect the glide angle provided the pilot uses the correct airspeed. Since it is the lift-over-drag (LD) ratio that determines the distance the aircraft can glide, weight does not affect the distance. The glide ratio is based only on the relationship of the aerodynamic forces acting on the aircraft. The only effect weight has is to vary the time the aircraft glides. The heavier the aircraft, the higher the airspeed must be to obtain the same glide ratio. For example, if two aircraft having the same LD ratio but different weights start a glide from the same altitude, the heavier aircraft gliding at a higher airspeed arrives at the same touchdown point in a shorter time. Both aircraft cover the same distance, only the lighter aircraft takes a longer time. However, the WSC aircraft has different characteristics because it has a flexible airframe. As more weight is added to the WSC wing, it flexes more, creating more twist in the wing, decreasing aerodynamic efficiency, as discussed in Chapter 2. For example, a pilot is accustomed to a glide ratio of 5:1 flying solo, a passenger is added, and this glide ratio may decrease to 4:1. This decrease in glide ratio for added weight is true for all descent speeds. The amount of decrease in glide ratio varies significantly between manufacturers and models because each wing flexes differently. The more flexible the wing is, the greater the decrease in glide ratio. Pilots should become familiar with glide ratios for their aircraft at all speeds and all weights. Although the propeller thrust of the aircraft is normally dependent on the power output of the engine, the throttle is in the closed position during a glide, so the thrust is constant. Since power is not used during a glide or power-off approach, the pitch attitude must be adjusted as necessary to maintain a constant airspeed. The best speed for the glide is one at which the aircraft travels the greatest forward distance for a given loss of altitude in still air. This best glide speed corresponds to an angle of attack resulting in the least drag on the aircraft and giving the best lift-to-drag ratio, max. Figure 6.16, any change in the gliding airspeed results in a proportionate change in glide ratio. Any speed, other than the best glide speed, results in more drag. Therefore, as the glide airspeed is reduced or increased from the optimum or best glide speed, the glide ratio is also changed. When descending at a speed below the best glide speed, induced drag increases. When descending at a speed above best glide speed, parasite drag increases. In either case, the rate of descent increases and the glide ratio decreases. This leads to a cardinal rule of aircraft flying that a student pilot must understand and appreciate. The pilot must never attempt to stretch a glide by applying nose-up pressure and reducing the airspeed below the aircraft's recommended best glide speed. Attempts to stretch a glide invariably result in an increase in the rate and angle of descent and may precipitate an inadvertent stall. To enter a glide, the pilot should close the throttle and obtain the best glide speed. When the approximate gliding pitch attitude is established, the airspeed indicator should be checked. If the airspeed is higher than the recommended speed, the pitch attitude is too low. If the airspeed is less than recommended, the pitch attitude is too high. Therefore, the pitch attitude should be readjusted accordingly by referencing the horizon. After the adjustment has been made, the aircraft should be retrimmed, if equipped, so that it maintains this attitude without the need to hold pitch pressure on the control bar. The principles of attitude flying require that the proper flight attitude be established using outside visual references faa-h-8083-5, then using the flight instruments as a secondary check. It is a good practice to always retrim the aircraft after each pitch adjustment. A stabilized power-off descent at the best glide speed is often referred to as a normal glide. The flight instructor should demonstrate a normal glide, and direct the student pilot to memorize the aircraft's angle and speed by visually checking the 1. Aircraft's attitude with reference to the horizon. 2. Noting the pitch of the sound made by the air. 3. Pressure on the controls and the feel of the aircraft. Due to lack of experience, the beginning student may be unable to recognize slight variations of speed and angle of bank immediately by vision or by the pressure required on the controls. The student pilot must use all 3 elements consciously until they become habits, and must be alert when attention is diverted from the attitude of the aircraft. A student must be responsive to any warning given by a variation in the feel of the aircraft or controls or by a change in the pitch of the sound. After a good comprehension of the normal glide is attained, the student pilot should be instructed of the differences in the results of normal and abnormal glides. Abnormal glides are those conducted at speeds other than the normal best glide speed. Pilots who do not acquire an understanding and appreciation of these differences experience difficulties with accuracy landings, which are comparatively simple if the fundamentals of the glide are thoroughly understood. Gliding turns have a significant increase in descent rate than straight glides because of the decrease in effective lift due to the direction of the lifting force being at an angle to the pull of gravity. Therefore, it should be clearly understood that the steeper the bank angle, the greater the descent rate. In gliding turns, the decrease in effective lift due to the direction of the lifting force being at an angle to the pull of gravity make it necessary to use more nose-up pressure than is required for a straight glide. However, as discussed earlier for steeper turns, airspeed must be maintained well above stall speed, which increases during turns, or the WSC could stall in the turn. When recovery is being made from a medium or high banked gliding turn, the pitch force which was applied during the turn must be decreased back to trim, which must be coordinated with the roll back to level. In order to maintain the most efficient or normal glide in a turn, more altitude must be sacrificed than in a straight glide, since this is the only way speed can be maintained without power. Attention to the front tube angle with the horizon and the reference point on the front tube provide visual reference of attitudes while gliding. Figures 6 to 17 and 6 to 18, common errors in the performance of descents and descending turns are: failure to adequately clear the area, inability to sense changes in airspeed through sound and feel, failure to maintain constant bank angle during gliding turns, inadequate nose-up control during glide entry resulting in too steep a glide, attempting to establish/maintain a normal glide solely by reference to flight instruments, attempting to stretch the glide by applying nose-up pressure, inadequate pitch control during recovery from straight glides. Pitch and power. No discussion of climbs and descents would be complete without touching on the question of what controls altitude and what controls airspeed. The pilot must understand the effects of both power and pitch control, working together, during different conditions of flight. As a general rule, power is used to determine vertical speed and pitch control is used to determine speed. However, there are many variations and combinations to this general statement. Decreasing pitch and diving do provide a quicker descent but is not typically used as a flight technique for long descents. Changes in pitch through moving the control bar forward and backward are used for maintaining level flight in rising and falling air, and pulling back on the control bar is used for a steep approach technique to lose altitude. However, these techniques are used only for short durations and not the primary altitude control for the WSC. The throttle is the main control used for determining vertical speed. At normal pitch attitudes recommended by the manufacturer and a constant airspeed, the amount of power used determines whether the aircraft climbs, descends, or remains level at that attitude. Steep turn performance maneuver. The objective of the steep turn performance maneuver is to develop the smoothness, coordination, orientation, division of attention, and control techniques necessary for the execution of maximum performance turns when the aircraft is near its performance limits. Smoothness of control use, coordination, and accuracy of execution are the important features of this maneuver. The steep turn maneuver consists of a level turn in either direction using a bank angle between 45 degrees to 60 degrees. This causes an overbanking tendency during which maximum turning performance is attained and relatively high load factors are imposed. Because of the high load factors imposed, these turns should be performed at an airspeed that does not exceed the aircraft's design maneuvering speed, VA. The principles of an ordinary steep turn apply, but as a practice maneuver the steep turns should be continued until 360 degrees or 720 degrees of turn have been completed. Figure 619. An aircraft's maximum turning performance is its fastest rate of turn and its shortest radius of turn, which change with both airspeed and angle of bank. Each aircraft's turning performance is limited by the amount of power its engine is developing, its limit load factor, structural strength, and its aerodynamic characteristics. Do not exceed the maximum bank angle limitation in the PO. For example, A maximum 60 degrees bank angle is a limit used by many manufacturers. The pilot should realize the tremendous additional load that is imposed on an aircraft as the bank is increased beyond 45 degrees. During a coordinated turn with a 60 degrees bank, a load factor of approximately 2 Gs is placed on the aircraft's structure. Regardless of the airspeed or the type of aircraft involved, a given angle of bank in a turn during which altitude is maintained always produces the same load factor. Pilots must be aware that an additional load factor increases the stalling speed at a significant rate. Stalling speed increases with the square root of the load factor. For example, a light aircraft that stalls at 40 knots in level flight stalls at nearly 57 knots in a 60 degrees bank. The pilot's understanding and observance of this fact is an indispensable safety precaution for the performance of all maneuvers requiring turns. Before starting the steep turn, the pilot should ensure that the area is clear of other air traffic since the rate of turn is quite rapid. After establishing the manufacturer's recommended entry speed or the design maneuvering speed, the aircraft should be smoothly rolled into a selected bank angle between 45 degrees to 60 degrees and the throttle increased to maintain level flight. Always perfect the steep turn at 45 degrees and slowly work up to higher bank angles. As the turn is being established, control bar forward pressure should be smoothly increased to increase the angle of attack. This provides the additional wing lift required to compensate for the increasing load factor. After the selected bank angle has been reached, the pilot finds that considerable force is required on the control bar and increased throttle is required to hold the aircraft in level flight to maintain altitude. Because of this increase in the force applied to the control bar, the load factor increases rapidly as the bank is increased. Additional control bar forward pressure increases the angle of attack, which results in an increase in drag. Consequently, power must be added to maintain the entry altitude and airspeed. During the turn, the pilot should not stare at any one object. Maintaining altitude, as well as orientation, requires an awareness of the relative position of the forward tube in the horizon. The pilot must also be looking for other aircraft mainly towards the direction of the turn while glancing at the instruments to make sure the airspeed and altitude are being maintained. If the altitude begins to increase or decrease, a power adjustment may be necessary to maintain the altitude if the bank angle and speed are maintained. All bank angle changes should be done with coordinated use of pitch and throttle control. The rollout from the turn should be timed so that the wings reach level flight when the aircraft is exactly on the heading from which the maneuver was started. While the recovery is being made, forward bar pressure is gradually released and power reduced, as necessary, to maintain the altitude and airspeed. Common errors in the performance of steep turns are: failure to adequately clear the area, excessive pitch change during entry or recovery, attempts to start recovery prematurely, failure to stop the turn on a precise heading, inadequate power management resulting in gaining or losing altitude, inadequate airspeed control, poor roll/pitch/power coordination, failure to maintain constant bank angle, failure to scan for other traffic before and during the maneuver. Energy management: the WSC aircraft has very little momentum because of its relative light weight as compared to airplanes. Therefore, it is important that pilots learn to manage the kinetic energy of the WSC. Higher speed and higher power is higher energy. Lower speed and lower power is lower energy. The ability for a pilot to maintain high energy levels in turbulent air and while near the ground is the basis for energy management for WSC. Energy management should faa-h-8083-5 be practiced at higher altitudes. While maintaining straight and level flight, power is increased and decreased, and pitch control must be used. The pilot should start at the trim position and with the appropriate cruise throttle setting. As power is smoothly applied towards full throttle, the WSC aircraft pitch attitude attempts to increase. The pilot should decrease the pitch to maintain level flight. This results in a high energy level. Once this application is held for a couple seconds, the pilot should then smoothly reduce power to the cruise power setting and increase pitch to maintain level flight. The WSC aircraft is now back to at a lower trim/cruise power and a medium energy level. Again, increase power and reduce pitch to stay level, attaining a high energy level. Now, reduce power to idle and as the nose lowers, increase pitch. The pilot must be aware of the decreasing energy levels occurring during this phase of the maneuver, for this is usually a precursor to accidents when approaching the runway. The pilot should recognize this scenario and promptly apply the power as appropriate to prevent the aircraft from descending. Additionally, the pilot must be aware of the slow flight and stall characteristics to prevent a stall and to maintain a specified heading. Once the student masters this maneuver successfully at higher altitudes, energy management can be practiced with low passes down the runway in calm winds at higher energy levels, then at the lower trim/cruise power medium energy level, and finally higher to medium trim/cruise power energy levels. Low passes over the runway fine tunes the student's skills for energy management and is an excellent exercise to prepare students for landings. It is important to understand that higher energy levels should be used while maneuvering near the ground, especially in turbulent or crosswind conditions. This is discussed in Chapter 7, Takeoff and Departure Climbs, that higher energy is recommended as the WSC aircraft lifts off and initially climbs out from the runway. Higher energy is also recommended for a power on approach where the airspeed is higher than the normal approach speed, and the power is higher than the normal approach power. There is still a descent rate, but the WSC aircraft has more overall energy to handle turbulence and crosswinds. Figure 620. Slow flight and stalls is discussed in Chapter 2. The maintenance of lift and control of an aircraft in slow flight requires a certain minimum airspeed and angle of attack. This critical airspeed depends on certain factors, such as gross weight, load factors, and density altitude. The minimum speed below which further controlled flight is impossible is called the stalling speed. An important feature of pilot training is the development of the ability to estimate and feel the margin of speed above the stalling speed. Also, the ability to determine the characteristic responses of the aircraft at different airspeeds is of great importance to the pilot. The student pilot, therefore, must develop this awareness in order to safely avoid stalls, and to operate an aircraft correctly and safely at slow airspeeds. As discussed in Chapter 2, the nose stalls while the tips keep FL-ying. Therefore, the definition of stall speed of the WSC aircraft is the speed at which the nose starts stalling. The control bar is pushed forward and buffeting is felt on the control bar as the root reaches the critical angle of attack. Separation of the laminar airflow occurs, creating turbulence that can be felt in the control bar. There is a loss of positive roll control as the nose buffets and lowers as it loses lift. Slow flight. The objective of maneuvering during slow flight is to develop the pilot's sense of feel and ability to use the controls correctly and to improve proficiency in performing maneuvers that require slow airspeeds. Slow flight is broken down into two distinct speeds, 1. VX and the short faa-L descent speed that was discussed earlier, and 2. Minimum controlled airspeed, the slowest airspeed at which the aircraft is capable of maintaining controlled flight without indications of a stall, usually 2 to 3 knots above stalling speed as discussed below. The minimum controlled airspeed maneuver demonstrates the flight characteristics and degree of controllability of the aircraft at its minimum FL-ying speed. By definition, the term flight at minimum controllable airspeed means a speed at which any further increase in angle of attack or load factor causes an immediate stall. Instruction in flight at minimum controllable airspeed should be introduced at reduced power settings with the airspeed sufficiently above the stall to permit maneuvering, but close enough to the stall to sense the characteristics of flight at very low airspeed, sloppy control, ragged response to control inputs, difficulty maintaining altitude, etc. Maneuvering at minimum controllable airspeed should be performed using both instrument indications and outside visual reference. It is important that pilots form the habit of frequent reference to the flight instruments, especially the airspeed indicator, while FL-ying at very low airspeeds. However, the goal is to develop a feel for the aircraft at very low airspeeds to avoid inadvertent stalls and to operate the aircraft with precision. The objective of performing the minimum controlled airspeed is to FLY straight and level and make shallow level turns at minimum controlled airspeed. To begin a minimum controlled airspeed maneuver, the WSC is FL-on at trim speed straight and level to maintain a constant altitude. The nose is then raised as the throttle is reduced to maintain a constant altitude. As the speed decreases further, the pilot should note the feel of the flight controls, pitch pressure, and difficulty of maintaining a straight heading with the increased side-to-side pilot input forces required to keep the wings level. At some point the throttle must be increased to remain level after the WSC has slowed below its maximum LD speed. The pilot should also note the sound of the airflow as it falls off in tone. There is a large difference by manufacturer and model, but the bar generally should not be touching the forward tube at minimum controlled airspeed. For example, the control bar would be 1 to 3 inches from the front tube at minimum controlled airspeed. Figure 621. The pilot should understand that when FL-ying below the minimum drag speed, L/Dmax, the aircraft exhibits a characteristic known as speed instability. If the aircraft is disturbed by even the slightest turbulence, the airspeed decreases. As airspeed decreases, the total drag increases, resulting in a further loss in airspeed. Unless more power is applied in it or the nose is lowered, the speed continues to decay to a stall. This is an extremely important factor in the performance of slow flight. The pilot must understand that, at speeds less than minimum drag speed, the airspeed is unstable and will continue to decay if allowed to do so. It should also be noted that the amount of power to remain level at minimum controlled airspeed is greater than that required at the minimum drag speed, which is also the best glide ratio speed and the best rate of climb speed. When the attitude, airspeed, and power have been stabilized in straight and level flight, turns should be practiced to determine the aircraft's controllability characteristics at this minimum speed. During the turns, power and pitch attitude may need to be increased to maintain the airspeed and altitude. The objective is to acquaint the pilot with the lack of maneuverability at minimum controlled airspeed, the danger of incipient stalls, and the tendency of the aircraft to stall as the bank is increased. A stall may also occur as a result of turbulence, or abrupt or rough control movements when flying at this critical airspeed. Once flight at minimum controllable airspeed is set up properly for level flight, a descent or climb at minimum controllable airspeed can be established by adjusting the power as necessary to establish the desired rate of descent or climb. Common errors in the performance of slow flight are: failure to adequately clear the area, inadequate forward pressure as power is reduced, resulting in altitude loss, excessive forward pressure as power is reduced, resulting in a climb, followed by a rapid reduction in airspeed and mushing, inadequate compensation for unanticipated roll during turns, fixation on the airspeed indicator, inadequate power management, inability to adequately divide attention between aircraft control and orientation. Stalls. A stall occurs when the smooth airflow over the aircraft's wing route is disrupted and the lift degenerates rapidly. This is caused when the wing route exceeds its critical angle of attack. This can occur at any airspeed and any attitude with any power setting. The practice of stall recovery and the development of awareness of stalls are of primary importance in pilot training. The objectives in performing intentional stalls are to familiarize the pilot with the conditions that produce stalls, to assist in recognizing an approaching stall, and to develop the habit of taking prompt preventive or corrective action. Pilots must recognize the flight conditions that are conducive to stalls and know how to apply the necessary corrective action. They should learn to recognize an approaching stall by sight, sound, and feel. The following cues may be useful in recognizing the approaching stall: positioning the control bar toward the front tube, detecting a stall condition by visually noting the attitude of the aircraft for the power setting, hearing the wind decrease on the structure and pilot, feeling the wind decrease against the pilot, sensing changes in direction or speed of motion, or kinesthesia, probably the most important and best indicator to the trained and experienced pilot. If this sensitivity is properly developed, it warns of a decrease in speed or the beginning of a settling or mushing of the aircraft. During the practice of intentional stalls, the real objective is not to learn how to stall an aircraft, but to learn how to recognize an approaching stall and take prompt corrective action. Though the recovery actions must be taken in a coordinated manner, they are broken down into the following 3 actions for explanation purposes. First, at the indication of a stall, the pitch attitude and angle of attack must be decreased positively and immediately. Since the basic cause of a stall is always an excessive angle of attack, the cause must first be eliminated by releasing the control bar forward pressure that was necessary to attain that angle of attack or by moving the control bar backwards. This lowers the nose and returns the wing to an effective angle of attack. The amount of movement used depends on the design of the wing, the severity of the stall, and the proximity of the ground. In some WSC aircraft, the bar can be left out, and as the nose stalls, the wing lowers to an angle of attack and keeps flying since the tips do not stall. However, even though WSC aircraft generally have gentle stall characteristics, higher performance wings may not be as forgiving. Therefore, during a stall, the control bar should be moved back to reduce the angle of attack and properly recover from the stall. The object for all WSC aircraft is to reduce the angle of attack, but only enough to allow the wing to regain lift as quickly as possible and obtain the appropriate airspeed for the situation with the minimum loss in altitude. Power application in a stall is different than an airplane. Since power application in a WSC aircraft produces a nose-up moment after a stall has occurred and the pitch has decreased from the control bar movement, power should be applied. The flight instructor should emphasize, however, that power is not essential for a safe stall recovery if sufficient altitude is available. Reducing the angle of attack is the only way of recovering from a stall regardless of the amount of power used. Stall recoveries should be practiced with and without the use of power. Usually, the greater the power applied during the stall recovery, the less the loss of altitude. Third, straight and level flight should be regained with coordinated use of all controls. Practice of power on stalls should be avoided due to potential danger of whipstalls, tucks, and tumbles, as detailed later in THS chapter. Power off, at idle, turning stalls are practiced to show what could happen if the controls are improperly used during a turn from the base leg to the faa-h approach. The power off straight ahead stall simulates the attitude and faa-h characteristics of a particular aircraft during the faa-h approach and landing. Usually, the first few practices should include only approaches to stalls with recovery initiated as soon as the faa-h buffeting or partial loss of control is noted. Once the pilot becomes comfortable with this power off procedure, the aircraft should use some power and be slowed in such a manner that it stalls in as near a level pitch attitude as is possible. The student pilot must not be allowed to form the impression that in all circumstances a high pitch attitude is necessary to exceed the critical angle of attack, or that in all circumstances a level or near level pitch attitude is indicative of a low angle of attack. Recovery should be practiced faa-h without the addition of power by merely relieving enough control bar forward pressure that the stall is broken and the aircraft assumes a normal glide attitude. Stall recovery should then be practiced with the addition of power during the recovery to determine how effective power is in executing a safe recovery and minimizing altitude loss. Stall accidents usually result from an inadvertent stall at a low altitude in which a recovery was not accomplished prior to contact with the surface. As a preventive measure, stalls should be practiced at a minimum altitude of 1,500 feet AGL or that which allows recovery no lower than 1,000 feet AGL. Recovery with a minimum loss of altitude requires a reduction in the angle of attack, lowering the aircraft's pitch attitude, application of power, and termination of the descent without accelerating to a high airspeed and unnecessary altitude loss. The factors that affect the stalling characteristics of the aircraft are wing design, trim, bank, pitch attitude, coordination, drag, and power. The pilot should learn the effect of the stall characteristics of the aircraft being FL-own. It should be re-emphasized that a stall can occur at any airspeed, in any attitude, or at any power setting, depending on the total number of factors affecting the particular aircraft. Whenever practicing turning stalls, a constant pitch and bank attitude should be maintained until the stall occurs. In a bank stall or if the wing rolls as it stalls, side to side. Control bar movement is required to level the wings as well as pull the bar back to reduce the angle of attack. Power-off stall maneuver. The practice of power-off stalls is usually performed with normal landing approach conditions in simulation of an accidental stall occurring during landing approaches. Aircraft equipped with trim should be trimmed to the approach configuration. Initially, airspeed in excess of the normal approach speed should not be carried into a stall entry since it could result in an abnormally nose-high attitude. Before executing these practice stalls, the pilot must be sure the area is clear of other air traffic. To start the power-off stall maneuver, reduce the throttle to idle or normal approach power. Increase airspeed to the normal approach speed and maintain that airspeed. When the approach attitude and airspeed have stabilized, the aircraft's nose should be smoothly raised to an attitude that induces a stall. If the aircraft's attitude is raised too slowly, the WSC aircraft may slow only to minimum controlled airspeed and not be able to reach an angle of attack that is high enough to stall. The position of the control bar at which the WSC stalls can vary greatly for different manufacturers and make/models. Some can stall abruptly when the control bar is inches from the front tube. If the aircraft's attitude is raised too quickly, the pitch attitude could rise above the manufacturer's limitation. A good rule of thumb is 3 to 4 seconds from stabilized approach speed to pull the control bar full forward. The wings should be kept level and a constant pitch attitude maintained until the stall occurs. The stall is recognized by clues, such as buffeting, increasing descent rate, and nose-down pitching. Recovering from the stall should be accomplished by reducing the angle of attack by pulling the bar back and accelerating only to the trim speed while simultaneously increasing the throttle to minimize altitude loss if needed. Once the WSC accelerated to trim speed, the control bar can be pushed out to return back to normal trim attitude and speed. If there is any rolling during the stall or the stall recovery, the control bar should be moved side to side to maintain a straight heading. It is not necessary to go into a steep dive in a WSC aircraft to recover from a stall. This only loses more altitude than required and should be discouraged. The nose should be lowered as necessary to regain a FL-ying speed and return to a normal FL-light attitude as soon as possible. Figure 622. Recovery from power-off stalls should also be practiced from shallow bank turns to simulate an inadvertent stall during a turn from base leg to faa-h approach. During the practice of these stalls, care should be taken that the turn continues at a uniform rate until the complete stall occurs. When stalling in a turn, it does not affect the recovery procedure. The angle of attack is reduced and the wings leveled simultaneously with power applied if needed for altitude control. In the practice of turning stalls, no attempt should be made to stall the aircraft on a predetermined heading. However, to simulate a turn from base to final approach, the stall normally should be made to occur within a heading change of approximately 90 degrees. After the stall occurs, the recovery should be made straight ahead with minimum loss of altitude, and accomplished in accordance with the recovery procedure discussed earlier. Whip stall and tumble awareness. As discussed in Chapter 2, the WSC aircraft does not have a tail with a vertical stabilizer similar to an airplane, and there is the possibility of the wing tucking and tumbling. If a WSC tumbles, this will most likely result in a structural failure of the WSC and serious injury or death to the pilot and/or passenger. It is most important for the pilot to understand tumble awareness and use all means to avoid such an occurrence. The pilot can avoid a tuck and tumble by flying within the manufacturer's limitations, flying in conditions that are not conducive to tucks and tumbles, obtaining the proper training in pitch stability for the WSC. Flying within the manufacturer's pitch and airspeed limitations is simply adhering to the PO/AFM limitations. Depending on the manufacturer, this could mean no full power stalls, not exceeding pitch limits of plus or minus 40 pitch angle, not FL-ying below the safe FL-ying speed and turbulence, etc. Manufacturer's limitations are provided for the specific C aircraft to avoid tucks and tumbles. Pre-flight preparation is the faa-h-8083-5 step to avoid the possibility of a tuck/tumble to avoid FL-ying in strong weather conditions. This could be strong winds that create wind shear or strong convective thermals that create updrafts and downdrafts. This weather analysis is part of the pre-flight preparation weather analysis. The second pilot decision regarding appropriate weather while FL-ying is to look at the environment during FLI to understand and evaluate the situation. Weather conditions should always be evaluated as the FLI progresses, with ADM used to determine the best outcome for the situation. This could be turning back or landing depending on the situation. As a student or pilot progresses, turbulence will be encountered. Use the procedures for FL-ying straight and level as shown in Figure 6.8. Use this exercise as a foundation for developing pitch control awareness to keep the wing managed with proper control bar pitch and throttle control. For high pitch angles, the PO may have specific C procedures that should be followed for the particular WSC aircraft, but the following general guidelines are provided. After reviewing the aerodynamic aspects of the tuck/tumble in Chapter 2, refer to the following tuck/tumble awareness and avoidance procedures. As defined in the aerodynamics section, a whip stall is a high pitch angle when the tips stall because they exceed the critical angle of attack. This can be the result of strong turbulence or power on stall, pilot-induced, or any combination of these factors. A pilot must avoid all of these factors to avoid the possibility of a whip stall resulting in a tumble, but the following procedures are provided for tumble avoidance in case a whip stall or a nose rotating down below the manufacturer's limitations is encountered. The aircraft rotates nose down. Figure 6.23, whip stall to phase 1, push the control bar out to the front tube and level wings while increasing to full power and keeping control bar full out to reduce overpitching. Figure 6.23, phase 1 to phase 2, if rotation is so severe that it progresses to phase 4 in the WSC aircraft is tumbling, the ballistic parachute, if so equipped, should be deployed. There are other weather situations in which the nose is not at a high pitch attitude, where the back of the wing can get pushed up and enter phase 1 without an unusually high pitch attitude or whip stall. If pitched nose low, increase to full power while pushing the control bar full out to reduce nose down pitching rotation. Generally, the control bar full out and full throttle create a nose up moment. It takes extremely strong weather conditions and or pilot error to tuck/tumble a WSC aircraft. Experienced pilots FLY all day in moderate turbulence, but building experience FL-ying in turbulence should be approached slowly and cautiously to determine the pilot and aircraft capabilities and limitations. A scenario the following is one example of a scenario that could lead to a tuck/tumble. It is based on a viable training program in one location but lack of experience in another location. A student obtains his or her pilot's license with the minimum number of hours for the pilot certificate. The new pilot trained soloed, and obtained his or her license only in conditions near the ocean where there was typically an inverted midday sea breeze with little to no convective turbulence thermals. This developed confidence for FL-ying in winds up to 15 knots but no experience was gained in thermals. In fact, the pilot was not aware that strong thermals could be hazardous. Now, with the new license, the pilot visits his parents in the middle of the high desert of Colorado. Unfamiliar with the local conditions, the new pilot gets a weather report of winds to 15 knots, something the pilot has experienced before. By the time the pilot arrives at the airport, discusses the situation with the airport officials, and sets up the WSC aircraft, it is 2 o'clock in the afternoon. The wind is generally calm but increasing to 15 knots occasionally. There are towering cumulus clouds in the sky surrounding the current airport, similar to clouds that the pilot had seen far inland from where he or she took instruction and soloed. The pilot takes off in relatively calm winds, but it is unusually bumpy air. Without any experience in the high desert or with thermal conditions, the pilot has misjudged the conditions and is FL-ing in strong thermal convection. The new pilot climbs out trying to get above the turbulence, which usually works near the beach because of the mechanical turbulence near the ground. However, the turbulence increases. As the pilot is climbing to a pattern altitude of 1,000 feet AGL at full throttle, the aircraft is pitched nose up while the pilot lets the force of the updraft raise the nose. Never has the pilot felt the nose rise with this type of force before. The pilot is shocked and disoriented at this high pitch attitude, but eventually lets up on the throttle. But now at an unusually high pitch angle, the WSC nose FLIES into the downdraft of the thermal. At the same time, the updraft is still pushing up on the tips of the wing while the downdraft is pushing down on the nose, creating a forward rotation with a weightless sensation. Before the pilot knows it, the wing is rotating pitch down for a vertical dive. Phase 1 in Figure 623, the student remembers from training that in a nose-down rotation into a steep dive the control bar is pushed full forward and full throttle applied and initiates this corrective action. The pilot reaches the vertical dive, but because of the corrective action the WSC aircraft recovers from the dive and proceeds back to land safely. What went wrong? What were the errors? How could this near catastrophe have been avoided? In a new area and unfamiliar with the conditions, the new pilot should have asked the local instructor or other pilots about the conditions for the day. Local WSC pilots are a great resource for FL-ing the local conditions, but pilots of any category aircraft are knowledgeable of the conditions and could have provided advice for the new pilot. This might have prevented the new pilot from attempting this FL-ite. Flying in a new environment and not understanding the power of midday thermals in the high desert should have forced the new pilot to scrap this midday FL-ite. The pilot should have started FL-ing in the morning when there is little thermal convection and gained experience and understanding about the weather in this new area. Better pre-flight planning should have been accomplished, especially in a new location. The pilot should have known to obtain convective information and realize it was going to be too bumpy for his or her limited experience. The pilot was accustomed to seeing towering cumulus clouds where he or she trained, but they were way inland and not in the normal FL-ing area. Here clouds were observed all around. Site observations indicated strong thermal activity. Observation of winds picking up to 15 knots and then becoming calm normally indicates thermal activity. The pilot was familiar with steady 15-knot winds, but did not understand that calm wind increasing cyclically to 15 knots indicates thermal activity. The pilot did not initially react to the updraft and result in high pitch angle properly because pitch management habits had not been developed. The pilot hit the updraft and allowed the force of the updraft to move the control bar forward, increasing the pitch angle while not letting up on the throttle immediately. Both the control bar forward and full throttle forced the nose too high, creating the high pitch angle and whip stall condition. At the same time, the WSC aircraft FLEU into the downdraft, starting the nose down rotation. If the pilot had reacted quickly, pulled in the bar while letting up on the throttle and immediately going into the strong thermal, the high pitch angle would not have been achieved and the strong forward rotation would not have happened so abruptly. After the series of errors occurred, the pilot finally performed the preventive action to avoid a tumble, from the basic training of if the WSC is at a high pitch angle and the nose starts to rotate down to a low pitch angle, increase to full power while pushing the control bar full out to avoid a tumble. Chapter summary: knowledge of the effects and use of the controls is basic to develop a feel of the aircraft and become accustomed to attitude FL-ing. This is the basis for all FL-ite maneuvers. The 4 basic WSC FL-ite maneuvers requiring pilot proficiency are: straight and level FL-ite, level turns, climbs and climbing turns, descents and descending turns. Once the basic maneuvers are mastered, the steep turn allows the pilot to achieve maximum performance from the aircraft. Energy management techniques provide the basis for FL-ing in different atmospheric conditions and introduce the student to precise pitch and power control. Slow FL-ite and stall provide the pilot an awareness of the ability of the WSC to FLY at the lower end of the WSC performance. Whip stalls and tumbles are unique to WSC FL-ite, and pilot awareness and avoidance is an important concept for WSC pilots to understand.